about scattering amplitudes via AdS CFT.
Okay, so thank you very much for the possibility to talk here. So today I have chosen like board talk, so we can discuss a little bit more. It may take me more than 1 hour then.
That's
but,
fine.
But okay, I hope that's not a problem. So, well, today I will be talking about scattering amplitudes. Via AdS CFT. Can you see from there? I don't think so. Well, I will try to write in these 4 words. So this is in a few papers. Mostly in this paper. And this. So please stop me at any time and ask me any questions, and I will try to do my best to answer. So first, the outline of the talk, I will start with some motivations, telling what we want to study and why. Then I will give some intro, mostly the gauge theory results. Then we will focus on the string theory setup of the computation. And we will proceed and we will compute the amplitude for the case of 4 gluons. Then, if I have time, I will talk something about scattering amplitudes versus Wilson loops. So, what we will be interested is in computing scattering amplitudes of planar, this is very important, n equals 4 super Yenny-Mills. So that is the theory we are going to consider. Why? Well, of course, in principle, we would like to consider scattering amplitudes in QCD or some more realistic theories, at least, but that is very hard. So the reason why we consider planar n equals 4 super Yenny-Mills is twofold. First, it can give us still some very non-trivial information about the scattering amplitudes of QCD. And there are 2 features that make the study of this theory much easy to deal with. So the first feature is the so-called AdS CFT duality that allows to study this theory at a strong coupling by means of a weakly coupled string sigma model. Sorry, maybe the first 20 minutes will be a little bit boring for the people who know the CFT and all these things, but sorry?
There were lectures here on that subject. So I guess most of the people.
Well, okay.
Not everyone who's here now was here at the lecture, so.
No, I'm not suggesting.
Okay. So, well, and on the other hand, a lot of, like Byrne and collaborators, did a lot of computations of these scattering amplitudes at weak coupling, and it seems to be that for some particular kind of amplitudes, the so-called MHB amplitudes, this will not play much of a role, in which I will say the fact whether the amplitudes are MHB or not. They seem to have an iterative structure. In particular, this iterative structure allows to compute one amplitude at some order in the loop expansion in terms of some lower order amplitudes. So the aim of this talk, what we will do, is to compute scattering amplitudes of this theory at strong coupling by using the AdS CFT duality. Okay, so I think there shouldn't be any question, but some questions or remarks. Okay.
Perhaps you could just say a little bit about what's known about this iterative structure of
Yeah, I will. This is the intro, the gauge theory results. Yeah, I will review now what is known. So, in the gauge theory, people has considered what they call it the color ordered leading n, that is the color of the number of colors, amplitudes. That is the full amplitude, usually the full amplitude for the scattering of n gluons, has some piece that depends on the color structure times this color ordered amplitude. And what they have studied is it happens that in the large n limit, the color structure and the kinematics factorize. And so what we are going to study is these color order amplitudes. It turns out that these amplitudes are infrared divergent. And we need to regularize them. I think I prefer to write putting it up.
So is the statement that that piece is the leading order in large n contribution to the, I mean, that all the other pieces of the amplitude are subleading in 1 over n or something like that?
Yeah, exactly. I mean, like this is for the, they are considering just the large n limit.
Right, but the other tensor structures that you could write down for the amplitude.
Yes, this is in the large n.
They would
Yes.
be suppressed by
Yes.
that.
Mm-hmm. That's correct, yeah. Sorry, yeah. I'm not very used to this. So maybe yes. So these amplitudes turn out to be infrared divergent, and we must regularize them. What people usually does is they use the so-called dimensional regularization. In which you consider the theory not in 4 dimensions, but in 4 minus 2 epsilon dimensions. Then these amplitudes will depend explicitly on this parameter epsilon. So we'll have. So this is the quantity that they talk about. In particular, by doing a lot of computations, I think that like Dixon and Byrne, there are a series of something like 15 papers on that. They have noticed that if they define a new amplitude by scaling the 3-level amplitude, by scaling out the 3-level amplitude, as follows, then this amplitude at some loop order can be written in terms of lower order amplitude. For instance, the two-loop amplitude for 4 gluons is basically the square of the one-loop amplitude plus some function times the one-loop amplitude computed at a slightly different dimension, 4 minus 4 epsilon, plus some constant. Epsilon is negative, yeah. You need to have epsilon negative. Plus some things of order epsilon. So the iterative relation looks like that. Based on this kind of computations, plus 2 very important things of scattering amplitudes. One is the infrared behavior. Sorry. Yeah, that is very important, this coefficient. I will talk in a second about this coefficient a little bit more. Because, you see, this is just a coefficient that depends on epsilon and the coupling constant. But at this point, it's not very, this statement is not very profound. It will be more profound in 5 minutes, but just 1 second. So this kind of computations, plus the infrared behavior of scattering amplitudes. The infrared behavior of scattering amplitudes is well known since the work of Sterman and collaborators, even in QCD. Plus something that they call collinear limits. That is, you consider a n-point function scattering amplitudes, and you take the limit where 2 of the momenta of the gluons become almost collinear. Then you recover the n-1 scattering amplitudes. Based on these things and in this kind of computations, they have actually proposed an iterative ansatz for all number of gluons, for any number of gluons, and any number of loops. And the ansatz looks as follows. So if you define the amplitude as 1 plus...
Sorry, just to understand the equation that you've written above there, are you saying that the expression, this expression plus there are additional pieces related to the infrared behavior?
No, sorry, no. I am very sorry. So this is one expression.
This is your formula?
Yeah, and this is the formula. Now, the authors, in order to propose the answer that I will write, used this formula plus a very similar formula for the case of 5 gluons, plus the well-known infrared behavior of scattering amplitudes, plus these collinear limits of scattering amplitudes. So they used all that information
to get an endpoint.
Exactly, to get an ansatz for the endpoints. Sorry. And the ansatz for the endpoints, if something is not clear, just stop me, or that's great. Is the following. So here alpha simply keeps track of the loop expansion. This is the n amplitude at L loops. And this is simply the exponential of the sum of alpha L up to things of order epsilon. The answer looks like this.
Alpha is something like lambda or pi?
Sorry?
Alpha is...
Yeah, it has some 4 pi, some powers of epsilon, but I am...
It's the Toft coupling, basically.
Yes, exactly. It goes with the Toft coupling. So
what is exactly the status of this expression? I mean, it's not a deduction from exact knowledge of the
No,
argument.
of course. Now I will tell you exactly where it has been
Yeah.
tested.
Yeah.
So, first of all, the question of today, what is the content of this? So the important property of these ansatz is that this function f and this constant c don't depend on the number of gluons, n, and don't depend on the kinematics. So if by doing explicit computations for 4, 5 gluons, you can compute these two functions, f and c, then you have an ansatz for the n gluons scattering amplitudes. Besides, this c doesn't depend on epsilon, and this f is something like f naught plus epsilon f1 plus epsilon square f2. So that is exactly what f means. This f naught will be the so-called cusp anomalous dimension. I will return to this before. Now, this the status of the problem, how much has been tested. I think it has been tested for 4 gluons up to 4 loops, and for 5 gluons up to 5 loops, up to 2 loops, and then up to 1 loop for every. But for 1 loop, it's not doesn't have any content because you just expand and it's just the first piece.
And these statements are purely for the, if you choose the helicities of the gluon, so it's MHV?
Yes, that is another point that I thank you very much. So this is for the MHV amplitudes. By MHV, you have gluons that have helicity plus or minus. 2 of the gluons have 1 helicity, and n minus 2 gluons have the opposite helicity. This, this will not play a role for what I will say, and I will comment why, but these are MHV amplitudes. So the full statement of this ansatz is that this function f and this c don't depend on the kinematics or on the number of gluons.
Do you have any combinatorial interpretation of this expression?
You can understand pretty easily the infrared behavior of this expression, but I don't know if I would call it combinatorial. I can just, sorry, a parenthesis in 1 minute. So something that you can see, for instance, can you see here, is that if you consider the scattering of n gluons, something like this, right? Then in the planar limit, the infrared part will come from soft gluons that go between one hard gluon and another hard gluon. The hard, I mean the gluons that you are scattering. So it turns out that in the planar limit, these soft gluons cannot go between this and this, but can go only between adjacent pairs. So this is like if you take the product of n times a single cusp. So that is all the combinatorics I can see it arises, but no more than that.
And those functions f are kind of interpolating between different regions?
Yeah, this f is a function of the coupling constant. And I will be a little bit more specific in a second. Any other question? So for us, what will be more important is the case of a scattering of 4 gluons. So in the case of 4 gluons, the amplitude looks as follows. So we have a 3-level amplitude. We have a divergent piece that depends on S, and a divergent piece that depends on T. Here, S and T are the usual Mandelstam variables for the scattering of 4 particles, times a finite piece. And this finite piece is a function f of lambda times the log square of S over T plus some constant that is not interesting for us. Whereas the divergent part is the exponential and has two pieces. Has a leading divergent piece that goes with 1 over epsilon squared. Epsilon, remember, was how far we are from 4 dimensions, times f minus 2. This is a function of lambda, and well, you don't need to care too much about this. But this is the infrared cutoff, the scale of infrared cutoff, and this is S. Plus another function, plus a term that is subleading in the infrared divergences that goes with 1 over epsilon. And this is controlled by a function that people calls G, also of the coupling constant. So the important characteristic of this amplitude, the thing that will be important for us, is that the divergent piece, this one, is characterized by two functions. This, that is so-called cusp anomalous dimension, and this is a function that is very well known, how it behaves from weak and strong coupling. It controls the leading divergent piece, and it controls also the finite piece. Notice that this function is the same.
Sorry, is this expression here supposed to be the n equals 4 case of the previous formula that you wrote down?
Yes, that's correct. But this is M. Yeah, this is Mn that, remember, was
defined.
An over A at tree level here.
You divide out the tree answer in
Yes.
Oh yes. So A becomes M times the tree. So that's why you
Exactly.
have tree level at the first part, and then.
So then you have, you can compute the amplitude at one loop, and you can see that
That's the log squared S over T.
Exactly, exactly. You get this finite piece plus some infrared part, and then.
What do you mean by upper index minus 2?
It's integral. Like the derivative, the double derivative of this is f.
Just the Taylor series of, yeah.
Yeah, lambda d lambda, like 2 times is simply f. Okay, any other further question?
Do people know that that function is the cosp anomalous dimension, or is that a guess?
No. Because, well, basically this thing that I have drawn here tells you that the scattering amplitude, and you know that like every 2 gluons, imagine this is a pizza, right?
Yes.
Then the pizza you can divide in n slices, and then each one of them looks like a cusp, like a Wilson loop with a cusp. And that's why the cusp anomalous dimension arises.
So that argument can be made order by order in perturbation theory?
Yes, because it has to do more with the planar limit.
Yes.
So mu here is some infrared scale which you introduced.
Yes,
with your
yes,
kind of chapter.
exactly. I mean, when you have dimensional regularization, you have epsilon and mu. And the scale, this is not very important, but the scale starts running because the theory is not conformal anymore in 4 minus 2 epsilon, so it will have some dimension. And well, this is what you would expect.
But if you compute some observable quantity, it should not depend on.
That's correct, yeah. These quantities, you are computing the scattering amplitudes. That's a very important point. You are computing the scattering amplitudes of these color ordered scattering amplitudes. This quantity is not infrared safe, it's infrared divergent. But if you were to compute a physical observable, then at the end of the day, the result has to be infrared safe, has to be independent on this infrared regulator. But this is like, you can consider them as amplitudes between the partons. So they are not the real asymptotic states of a theory. You have also color indices. So this is not gauge invariant even.
Do you know that from this particular expression you can extract a physical observable which relates, let's say, to the bit which is independent of that side?
If you know that, Well, I mean, yeah, I don't know if anyone has tried to compute. Well, F is definitely a physical observable. There are some things that you can measure and you can extract F. But this should be seen as some intermediate step. I mean, like when you want to compute scattering amplitudes, like you are at LHC and you want to compute jets, like two jets going into two jets, and suppose that QCD is not the theory, but n equals 4 is the theory, but apart from a lot of problems we would have. But then this would enter as intermediate part. Actually, the amplitudes that you have to compute are these kind of full amplitudes, and then you have to play with all the color factors. So I think there is a pretty long way. But these amplitudes should be seen as intermediate steps in order to compute. But definitely this like finite piece will probably survive when you compute some physical quantity. Okay, so in this talk, I think what we will do is we will use AdS CFT duality in order to compute these scattering amplitudes at a strong coupling. So AdS CFT duality, as you may know, is the equivalence between this theory, n equals 4 super Yanni-Mills, and type 2B strings on AdS 5 cross S5. In particular, the duality has a dictionary between the parameters of both theories and relates lambda to the radius of curvature of AdS in string units. So you see that you can study this theory at a strong coupling by studying a weakly coupled sigma model. Now, okay, in the following, I will first set up the computation, and then we will do actual computations. In order to set up the computation, we will use a deep brain as infrared regulator. But in order to do actual computations, because it's the only thing we could do, and then because we want to compare with gauge theory anyway, we will introduce the analog of dimensional regularization. And then we will proceed and we will make this computation for the case of 4 gluons.
Equally simple to work with.
Yeah, maybe this different. I mean, we didn't think hard enough because the most thing, I mean, like our main point was to compare our results with the result of the gauge theory. So
Sure, but gauge using dimensionalization is an artifact, and nothing should depend upon it.
that's fine, yeah. But all these recurrence relations and all that exists for. Another popular regularization is to give a small mass to the gluons, for instance. On that case, well, one could imagine how to extend that to the strong coupling side. I can mention
Well, the other
that.
thing is to take the external things off shell. I'm not sure that's quite the same.
Yeah, I was meaning that. Yeah, to take the external gluons of shell, a little bit of shell. But I don't know if yeah, but well, we knew like the BDS ansatz was our main motivation, and this is computed using dimensional regularization. So okay, so let's start setting up the computation. So what we will do, okay, we want to consider the scattering of gluons. It's not even clear how to define gluons at a strong coupling. What are we scattering? So what we do is first start with the metric of AdS 5. And then put a D3 brain just by hand at some large distance C equals to some C infrared. So that is our infrared cutoff. That is how we regularize things. This should not be confused with the point c equals 0. So we have c equals 0 here, and we put this debrane at c equals c infrared, and it's very large. Then we will have asymptotic states that will correspond to open strings that end on this debrane. And what we are considering is the scattering of these open strings. Yeah, to recover, you see, I mean, at this level, at strong coupling, we are not interested in that. But at subleading, yes, that's correct. I mean, I think that you need a lot of brains, and then suppose you have, then this string will come between this and this one, and will scatter with another string that comes between this and the first one. So you will need to consider that situation. Yeah, that's correct. But in what we do, we consider the scattering of this.
So this is more like the scattering of the photons that you would get if you broke SUN down to U1 cross SUN minus 1.
Yeah, that's sounds
Literally that.
Exactly. That's yeah, that's correct. Yeah. So the important point of this scattering is the following: is that suppose that you have some fixed momentum k in units of the gauge theory. This k is the conjugate momenta to this coordinate x here. Then the proper momentum would be equal to c infrared times this k. And as c infrared is very large, because it's some infrared cutoff, it's some large distance, this is very large. It's much larger than 1, well, in some units, right? So what we are considering is the scattering of strings at fixed angle with a very large proper momenta. Notice that, well, just I will comment on something in a few seconds. So this was already considered in flat space. So we have the scattering of strings with large momenta. At fixed angle. And this was considered in flat space by Gross and Mende. And the key result of their computation was that the amplitude can be approximated by a saddle point of the action. So you don't need, if you want to compute the amplitude, you don't need to compute, with knowing the saddle points of the action is enough. So what we will need to consider in our case is classical strings on AdS. Notice, by the way, that the result of Gross and Mende is valid only when the Mandelstam variables are very large. But for us, that is not necessary, because for every finite k proper momenta will be large. So we don't need it. So the warping of the space help us to, for the saddle point to be a good approximation. Is there any questions?
Why are you not taking the supergravity limit?
We will. Yeah, it's the supergravity action. Yeah.
But this must only be valid in the limits of large coupling, right? In the calculation.
Yeah, yeah. This is yeah, that's correct. This will be valid only. We want to know only the leading strong coupling value of this amplitude.
And the position of the brane, Z equals ZIR. So you have to take the brane if you want to reach this gross Mendel region. You have to take ZIR to be very large, according to that formula, right?
Yeah, this CIR is large.
So does that mean it's near the boundary or near the horizon?
No, that is better. Near the boundary is at C equals 0. So it's on the other.
So taking away your infrared regulator corresponds to moving the brane towards the horizon. Is that what you're saying?
Towards C equals infinity, yeah.
Yes.
But now I will, in 5 minutes I will change variables anyway. But yeah. So, yeah, that's why. Okay, so what we need to consider then is, suppose we have the scattering of n particles.
Just a second. So,
Yeah.
So the infrared regulator is taken to infinity to 0. So the mass of
C infrared is going to infinity.
so the mass of the gluons is
0. Yeah, that is an important point. So the mass, this infrared goes to infinity. So the mass of these open strings goes to 0. And that is fine because it corresponds to gluons.
They're at 0 anyway, aren't they? Because they're, I mean, if the strings are ending on the same D brane, then
Yeah, that's true.
0.
Sorry. Yeah. Now, yeah, what I wanted to
There
say.
must be strings stretching from the horizon or something.
Yeah. No, sorry, yeah. Well, what I wanted to say was a little bit different. Indeed, I mean, this the mass of these particles is 0.
Right.
Yeah, but somebody once asked me, like, you could do very much this computation with particles that goes between that live here, like a string that goes between this and this, like usually Wilson loop computations in a AdS CFT.
From the stretching from the boundary to the D brane.
Yeah, exactly.
Yes,
And
right.
that corresponds to some kind of infinitely massive quark.
Right.
Whereas this
External-
corresponds.
external sort
Yeah,
of colour.
exactly. Yeah, sorry, I was confused.
So when Z goes to infinity, that string is becoming infinite. Those particles are becoming
Exactly.
infinitely massive rather than.
Yeah, it's not relevant for us. But somebody was asking me why you consider the open strings here instead of something like the usual Wilson loop, because a Wilson loop is like an infinite quark, an infinitely massive quark. But okay, let's.
I think in these coordinates it's more like 1 over z is actually right.
Yeah, now I will change coordinate, but just just say in 5 minutes. So we need to consider classical strings on AdS. So we will have a worksheet that has the topology of a disk with vertex operator insertions that corresponds to the particles, right? So for instance, we can have like 1, 2, 3, 4. And then the boundary conditions should be such that near each of these vertex operators, the momenta of the external states, of the states we are scattering, fix the form of the solution, fix the form of this worksheet. Besides, on the boundary of this worksheet, the C coordinate has to be equal to C infrared.
Fernando?
Yes.
Can I still go back to this picture? Because
Yeah.
so the usual D-brane picture when you think about string stretch, it's really an R coordinate, which is 1 over z. And the length of a string is at R, which is 1 over z. So
Mhm.
that R to infinity really means mass of a straight string goes to 0. So the string stretch from the boundary to this probe.
The mass of a string stretch from the boundary to this
To the
probe.
probe, yes.
goes to 0,
Yes, in this limit, because
even though the brain is not being taken towards the boundary, it's been taken towards the horizon. That's the confusing.
I think it goes to infinity, right?
That's the thing that
Well, it's not relevant for this, but I think, like, yeah, I think,
okay,
well,
well,
yeah.
I'll leave it.
Yeah, anyway, the mass of this fluence is 0, as it should be. So we have so we have to compute classical strings on AdS. So we will have a worksheet that has the topology of a disk with vertex operator insertions. And the boundary conditions are such that the worksheet is fixed near each of the insertions, and C has to be C infrared, that is very large, on the boundary. Actually, in order to put easier these boundary conditions, we go to the so-called T-dual variables, that all the discussion will be centered on these variables. That's why that are defined as follows. So if you have some metric that looks as following, then the T-dual coordinates y, and this T-dual, I should call it something like T-dual because the coordinate x is not compact. Like usual Bascher rules for T-duality. Then the boundary conditions will be as follows. If x mu carries some momentum k mu, then y mu will have some winding that will be proportional to this k mu. What do exactly I mean by this? I hope will be clear in 5 minutes. But this is a little bit of cue. But just before proceeding, notice that if in addition to this, to go to T-dualizing in these coordinates, in the x coordinates, we perform the following change of coordinates. We go to some little r, that is capital R squared over C. Then we end up with, again, the same AdS5 metric. But now written in terms of this coordinate R and the Y coordinates. Right? Okay, now we will have the worksheet, right? So now how is our worksheet? What happened with our worksheet? The worksheet will end, its boundary will be located at some R that is equal to R squared over C infrared, and ends on a line that is constructed as follows. And now will be clear the meaning of that. So the input, imagine we draw this the space, this space. Okay, so what, and suppose we put here the time direction, y0, and this is the direction y1, and this is the direction y2. So now what we do is, for each particle of moment that we want to scatter, of momentum k mu, we draw a segment that joins 2 points that are separated by 2 pi k mu. For instance, suppose we are scattering a particle with for momenta like 1, 1, 0, 0. Then we have to draw, sorry, some fancy. So we have to draw this line. Notice that as we are considering gluons, this line is lie-like.
So you're T-dualizing in all the coordinates parallel to the brain?
Yes, that's true.
Right.
Yeah, the brain, sorry, I didn't mention maybe. This brain extends along this
so
3 plus 1.
performing that transformation just for those parallel coordinates?
Yes,
Right.
yes. And we are T-dualizing the x, and we are taking this change of coordinates in C.
Right, but that's not it.
No, no, no.
Not T-dualizing.
No, 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 no. We are,
So the Neumann boundary conditions in those directions get turned into sort of Dirichlet boundary
Yes.
conditions by T-duality. So
yes,
that's why
yeah,
you're ending on particular
exactly.
surfaces.
Exactly. That's, yeah, indeed. And the particular surfaces are this one. So,
Sorry, I'm still confused. Why haven't you just written down the DBI action for that D3 brain, read off the Feynman rules, and immediately written down this action?
well, if you can do that, maybe.
Isn't it just 2 lines?
You can't do that. I mean, that's only the answer in some kind of if the brain is in AdS, right?
Well, but the
Then you have
AdS
to calculate the.
Yeah, but there'll be some metric factors in the DBI action.
Mm.
There'll just be, some function of ZII and capital R.
You need all the alpha prime corrections. The
Yeah.
action.
Right? Because here we are using the sigma model, so we.
I thought we were at large N and
Not large n is fine. Well, we will compute.
No, alpha prime corrections correspond to large lambda.
I mean,
Large lambda gets
yeah, exactly. I mean, like here you have large lambda.
Are you scattering? You're scattering. Well, you're scattering the massless modes of the open string.
Yeah, of this one. Yeah, basically. And it's not what we will do at the end of the day when we want to do an actual computation. This was our inspiration for the procedure.
But it must be in a regime where the low energy effective action on the brain isn't adequate. And
Yeah, maybe.
You must,
Well, this is the.
you must need.
Here the proper momentum is very large.
Right.
Exactly, this is indeed low energy effective action. Well, we're talking about training.
Yeah, and the proper momentum is large.
But this is not captured by the Bordenfeld action on the brain.
Yeah,
Right,
exactly.
okay, right.
Mm-hmm. So, okay, so for each particle that you want to scatter, you have to draw this line, and then you have to concatenate the lines according to the insertions on your disk. So for instance, for 4-point functions, you will have this, you will have like this like, you will have one on the edge above, and you will have this. Is clear what I am drawing? It's just the diagonal of the 4 sides of this cube. Then, now what happens? When we take the infrared regulator, see infrared, to infinity, the boundary of this worksheet is located at r equals 0, right? Because remember that r was roughly the inverse of C infrared.
And once again, that means the horizon, not the boundary of AdS.
Yeah, well, depends on which of the two AdS, because you see that you have AdS and these T-dual coordinates.
AdS, it's the
And the AdS of these T-dual coordinates. And the things are exactly the opposite. Yeah. So it's the boundary of this one.
right. And
So-
the horizon of the other. Of the
Yeah.
original.
So notice, and related with your comment, that this is exactly the same computation as you would do if you want to compute at a strong coupling by using AdS CFT the expectation value of this Wilson loop. Right? So what you are instructed to do is you draw your Wilson loop in the boundary that corresponds to r equals 0, and then you have to find a surface, is a minimal surface, because we have seen that the saddle point approximation is good, that ends on this boundary, on the Wilson loop formed by concatenating this sequence of Lie-like segments. So what we are saying, all what we are saying, is our prescription would be the following. What we are saying is that the leading exponential behavior of the amplitude is given through some relation that looks like this by the area of the minimal, surface that ends on such sequence of Lie-like segments. Notice that through the boundary conditions, we will have the information of the momenta of the gluons. So that is what the prescription is saying.
So you've drawn 4, but this holds for n.
Yeah, this calls for n. I just, well, in the paper we have the picture also for 6. But yeah, but you can have any n. So you give me a lot of gluons. You tell me what the momenta of those gluons are. You draw this surface, and then the minimal surface will give you the scattering amplitude at a strong coupling. That is.
So the justification why you look at saddle point is large lambda, not large momentum.
Well, it's large lambda, but also the fact that the proper momenta, not momenta in gauge theory units, but the proper momenta.
More intuition rather than.
Well, you cannot choose anyway. I mean, for any finite k, the proper momenta will be large anyway.
So for the Wilson loop computation, you only need large lambda to
Yes.
get a classical
Yes.
surface.
Yes, but it also depends what you fix. Yeah, fixed.
Yeah, this k don't need to be large. That is why what you say is.
That space, you
yes.
don't have anything to fix. You have alpha prime over.
Yeah. In flat space,
Square.
gross and Mende, this k have to be large.
Right.
S and T, let's say, for scattering amplitudes. Here, they don't need to be large. So, yeah, at the end of the day, the only thing you are using is that lambda is large. You don't.
Essentially, you have 3 scales: R, alpha prime, and K. If you set alpha prime, well, in flat space, you don't have
2. Well,
You have only 2.
yeah.
So you have only 1 ratio.
yeah.
That's why you need this special limit.
Momentum much larger
Yeah.
than the string scale.
Yes,
to get
exactly.
Yes, exactly.
Exactly.
Here, it's as long as the geometry is large.
Yeah, because the warping of the space is helping you to do that. So that is our prescription. Okay, so now, well, if there is no more questions, I will proceed and compute for 4 gluons. Any other question?
But by turning it, you've already taken the momentum to infinity by
The
turning
proper.
the problem into the proper momentum. You've
Yeah.
already taken to infinity in this problem
Yes.
by turning it into a Wilson loop computation. So
Yes. But it will work. This will work for any finite k.
then you wouldn't have your brain at the. Oh, it's any fixed. Okay.
Any fix. Yeah. Of course, maybe if you take k of the order of 1 over exponential of lambda, maybe something wrong will happen. I don't.
So far, this brain is still sitting at some small distance from the boundary. R, right?
No, okay, this will come later. But if you take this infrared to infinity, then this is exactly the same computation as you will do if you want to compute the expectation value of some Wilson loop. Yeah, this will be important for what I will say later. So, okay. So now let's see if we can find some of these classical solutions. So maybe. So shall I, because shall I simply put what the solution is, and
Well, maybe you could say a few words about how you found it.
Yeah, well, a lot of inspiration. No. Yeah, okay. So, okay, so for the case, suppose we imagine we have 4 gluons. I think I can erase here. So in that case, the diagram will be very similar to this diagram. So we have to find an action. We have to find a worksheet. We can, first of all, write down the Nambu-Goto action. In order to write down the Nambu-Goto action, the easiest thing to do is consider point-correct coordinates, r, y0, y1, and y2. So now we are considering this, and suppose that we define the usual Mandelstam variables s and t. Then, by using point-correct coordinates, we found it convenient to parameterize the worksheet by its projection to the y1, y2 plane. And it's not so hard to see that if S is equal to T, then this is a perfect cube, and the projection to this plane, y1, y2, is a square. So, what we will have, how we parameterize, so the Nambu-Goto action will be an action for 2 fields, r and y0.
Doesn't the interesting part of the BDS amplitude vanish if S is equal to T? Because
Yeah, that's a very good point.
it's 0.
Yeah, that's true. And we will come back to that later. Yeah, that's indeed a very good point. Indeed, it's like the most interesting part, because this log S over T will vanish. Okay, but this is generic. I mean, so in general, the Nambu-Goto action will be an action for 2 fields, r and y0, that will be function that will live on a plane. This plane will be a square, but if S is different from T, will be a rhombus instead of. In general, this distance is square root of T, and this distance here is square root of S. So shall I write the Nambu-Goto action? No, it's not. No. Okay. So now, so we want to find the surface, and the questions of motion coming from the Nambu-Goto action should be supplemented with the appropriate boundary conditions. Let me tell you that once you have computed the Nambu-Goto action, this Nambu-Goto action is the same for every process that you want to consider. So you have some equations of motion, and suppose that we put this square to plus minus 1. So we put the edges of the square in y1. So this is y1 and this is y2. So the boundary conditions are that r, for instance, vanishes at plus minus 1 and every y2, or any y1 and plus minus 1. So these are the boundary conditions. And in addition, the time coordinate, y0, along these lines has to go up and down, as this figure shows. In the literature by Krunchensky, he already had given the solution corresponding to a single cusp, so that served us as inspiration. But one can actually check that the following satisfies the boundary conditions and is a solution of the equations of motion.
Shouldn't, if y2 is 0, shouldn't y0 equal y1 according to your picture?
Sorry?
Suppose y2 is, in this picture, if y2 is 0.
Well, maybe you must rotate the picture. Now, in this picture, we are putting the origin here, and we are putting like 1 and minus 1 here.
Ah, okay, so
So the origin.
the boundary is at y2 equals not 0, but it's
But 1.
minus a half. Or, right.
Plus minus 1, yeah. I have chosen.
So then you get a linear. Y0 is equal to
Yes.
minus y1 or
Yes.
plus y1. Yeah.
Once you have found the solution in these coordinates, you can shift, you can do whatever you wish. But okay, we have seen that this is a solution of the equations of motion. This solution has a problem, as Nick was saying, that is a solution only, some question about this solution? I mean, it's just, now we go to action, boundary conditions, you plug it and you see it works and it satisfies the boundary conditions. But it has the problem that this is a solution only for the case S is equal to T, right? But in that case, remember that the amplitude, see over there, has a piece containing the log square of S over T. So, well, we needed to find the solution for S different from T. A very good thing, a very interesting thing, is to go to the so-called embedding coordinates.
So, but there should be some prediction from this, the fact that log S over t vanishes for this value, that the area of this, that's saying that there's no exponential suppression.
Yes, but then,
That's lambda. goes-
no, because you have the constant C. And this constant C can depend on lambda.
So dependent on lambda.
Yeah, it doesn't depend on the kinematics of the gluons. There is something you can compute. And for instance, the strong coupling value of this function G that was not known. You can also compute the strong coupling value of this function F, that is pretty well known. But we wanted to catch this. Because as I already told you, like this is already fixed by the infrared structure of the amplitudes. So we wanted to consider S different from T. Actually, if one goes from Poincaré to embedding coordinates, everybody knows what embedding coordinates are. Oh, okay, sorry. Okay, so in embedding coordinates, you suppose AdS 5, you parameterize it with 6 coordinates with this constraint. Yeah. So in these coordinates, there is isometries that form the group SO2, 4 that are conformal transformations. And one can write a relation between the Poincaré coordinates and these global coordinates.
Is it safe to use the same these
Well, maybe no, maybe it's not safe. So let's call it X if you wish. Yeah. Now, going from these coordinates to embedding coordinates, we notice that the equation for this surface is simply this one. So it's easy to see. Here you have 6 coordinates. Here there is 1, 2, 3, 4 constraints. So you have a 2-dimensional surface. So the equation for this surface in embedding coordinates is this one. Then we notice that if you do conformal transformations in embedding coordinates, what you do is you change the distance between these points. So we take the original solution. We perform boost transformations, in particular a boost in the 0,4 dimension, in the 0,4 direction, and then you get the general solution for S different from T.
So this is more like conformal boost.
Yeah.
But is it actually possible to see on the gauge theory side that you can change S over T by?
Well, yeah, there is some, there is what they call now. Then they started to call this like dual conformal symmetry. I mean, the fact that you start from a solution that had S equals T, then we applied conformal transformations on this solution, and we ended up with another solution.
You're saying this SO24 is actually not the same as the SO.
Very good.
Is that what you're saying?
Yes, this is SO24 of the dual coordinates.
I can't remember. In the original conformal symmetry, if you have a 4-point amplitude, then there's a conformal invariant called a cross ratio. Which must be, I mean, conformal transformations in 4 dimensions, can they change the Mandelstam variable? Can they change S over T, or is that invariant under those?
They are invariant cross ratios.
So S over T is a cross ratio, which is invariant. So it's a new symmetry that you've got on this
The,
side.
the point is the following. The point is, well, I don't want to enter much into the details, but the action, indeed, the action should be conformal invariant. So K applied in the original variables, K applied to the amplitude should be 0. So the amplitude should be a constant, and it's a constant, infinity. The point is that when you introduce epsilon, you have other ratios that you can make, like mu over S and mu over T.
Yes.
And that gives you this complicated behavior. So, well, I don't want, but this is some. So, okay, then I think we found the solution, right? We wrote it in global coordinates. Then in global coordinates, we noticed that if we apply conformal transformations, these conformal transformations are on these T-dual variables, should not be confused with the original variables. We can obtain the general solution for S different from T.
So what is the status of that SO24? I mean, it's not an exact symmetry of
No, they have seen this as a symmetry also at weak coupling. Well, maybe I talk about this a little bit later. But also weak coupling, they have seen, it's not known at 17 loops whether it's a symmetry or not. There are some,
So what you just said, that this solution is actually equivalent. There is, if you don't have any cutoff, the 2 solutions are equivalent.
Yes.
So you can go from S equal T to S not equal T.
Yeah, this is without any cutoff.
Yeah, but once you have a cutoff, they become inequivalent.
Yes, that's correct, yeah. It will not be too much relevant, but indeed, because this cutoff breaks conformal invariance. So you don't have this conformal symmetry anymore. Okay, now we have the solution. We can plug the solution into the action, and we can see what we get. Of course, we get infinity, right? Because, so now, once we have found this general solution, shall I write the form of the solution? I don't think. Well, like for instance, R. Well, like this gets bigger, and then you have like the parameters S and T enter into the solution, basically. But you see that it is still that R, instead of vanishing over a square, vanishes on the lines of a rhombus, and this is square root of T, and this is square root of S. So you can, if you wish, you can go back from embedding coordinates to Poincare coordinates, and you can find a pretty ugly expression for R in terms of y1 and y2. Okay, now we have the solution. We can plug it into the action, and we see what is our prediction for the amplitude. The problem is that the area diverges. And that was to be expected, because we took C infrared to infinity. So we have taken the infrared regulator. So what we want to do now is to introduce the analog of dimensional regularization. That is, to consider a theory in 4 minus 2 epsilon dimensions. In the gauge theory, what people does is they start with n equals 1 in 10 dimensions, and then dimensionally regularize to 4 minus 2 epsilon. But that is exactly in the case in which this epsilon, 4 minus 2 epsilon is integer, the theory living on a dp brane, where p is d minus 1. So what we will do is, instead of using the AdS 5 metric, we use the near horizon metric of a dp brane. And we suppose that this p can be 4 minus 2 epsilon. We analytically continue on this. So the important part of the action of the so instead of AdS 5, we will have this metric and this h, where is some constants that depend on d times r a minus d. And for instance, well, and d, remember, is 4 minus 2 epsilon. So, okay, now we can compute again the Nambu-Goto action, but now with this slightly deformed metric. And what we found is that the action, now with this epsilon dependence, is square root of lambda times some constant that will depend on epsilon. The Lagrangian density at epsilon equals to 0 over r to the epsilon. So this is the new Nambu-Goto action.
If you continue a D3 brane metric away from 4 dimensions, in other words, you continue dp where it's a dp brane, p where it's a dp brane, don't you introduce some kind of a running dilaton and other? I mean, because
Yeah,
only for d exactly.
that's true. At a strong coupling, it won't matter.
Uh-huh.
Yeah, but at subleading, you may have it. That's true.
So if you want to have if you want to continue a solution of Einstein's
Yes,
equations
yes.
in all those different dimensions, it's
Yeah, and indeed, Arkady can tell you that it's not easy to compute subleading corrections to this if epsilon. I mean, to expand in lambda and with dimensional regularization is not clear. So this is only at a strong coupling.
You're continuing this view theory. So
No, we can start with the original.
because
I mean,
from the original,
yes,
that
from the
would
very
mean-
beginning. Yeah.
That would mean you have your gluon sitting at horizon. You can brain constrict that horizon, and then you continue to
Yes.
epsilon development.
Yeah. So this introduction of r to the epsilon will have two effects. A good effect that now the integrals will converge, and a bad thing because now the equations of motion will depend on epsilon. And we were not able to find the solution of the equations of motion for general epsilon. But I can show it, but it will take me like 15 minutes. It turns out that it's enough for our purposes to take the zero order solution, the original solution, and to plug it into this action. We did that. We plugged that. We computed these integrals. And the final answer for the S are some things that depend on epsilon, some functions of epsilon. And then, well, in particular, you get, for instance, some kind of hypergeometric functions. But are integrals that can be done in a couple of days. It's not so difficult. Plus a factor of 1/2. Then, okay.
So this is somehow the result that this is only correct at leading order in
Epsilon. Yeah, exactly. That is
So
important.
you can only keep the leading part.
Yes,
small,
yes,
small,
yes.
right?
You may have at higher epsilon. If you want corrections at higher epsilon, you would need to find
Right.
the exact
Right.
solution. But for what we wanted to know, that was only up to epsilon to the 0 order, is enough. Well, there is a subtlety, like you wouldn't get this one up, but I don't want to enter.
Finite terms in this way.
Sorry?
Don't you miss some finite contribution by taking the solution for epsilon equals 0 and then?
Okay, I can be a little bit more precise in 1 minute now. So what we do is we take the 0 order solution, but taking into account the corrected solution near the cusps. And near the cusps, the corrected solution is known. I mean, we have seen how to extend the solution. We couldn't find the generic epsilon solution for the 4 cusps, but for the single cusp, you can.
That's enough.
Yes, and that's enough for getting the finite piece correct. Okay, we have everything. Let's expand in epsilon. So what we got was that the amplitude was something like the exponential of some divergent piece plus square root of lambda 8 pi plus some constant that doesn't depend on the
Divergent is poles and epsilon.
Sorry.
Divergent mean poles and epsilon.
Yes, now I will be a little bit more precise. Or maybe I wrote it everything here. And for divergent, we get a pole in epsilon and a piece that is linear in epsilon, in 1 over epsilon. And the same square root here. Okay, so this is our string theory computation, and this result we need to compare with that gauge theory result. So some things that we can see is that the divergent piece exactly matches. The strong coupling result for this function f was well known. And if you plug it, you see that the coefficient is exactly matching. On the other hand, from this computation, you can extract the strong coupling value for this function g. And using the strong coupling result for f, we see that the coefficient in front of the log square of s over t is exactly the one that we wanted.
Nobody does it. I mean, previously there's no interpretation of G as some kind of an anomalous dimension of an operator. There's no,
Yeah, it's some kind of collinear anomalous dimension.
there's no prediction
At the strong coupling, no.
for the strong coupling.
No.
Right.
I don't think you can. I think the biggest problem is that probably it's not the anomalous dimension of any operator.
Yeah.
Okay, so it's
You can stop in there.
well, yeah, I could go on if you wish for 15 minutes, but maybe I don't know if I may stop
Say a
here.
few words of conclusion, perhaps.
Okay, so well,
Jim was going to be.
okay, so
That's a very nice place to
yeah, exactly.
round it off.
So as you see, we have given procedure to compute the scattering amplitudes at a strong coupling. We could find the classical solutions for the case of 4 gluons, but the procedure in principle works for any number of gluons. One of the motivations would be to test the BDS conjecture for a higher number of gluons. And in particular, in the last of those papers, we consider a configuration with infinite number of gluons, in which you do a zigzag path of gluons in such a way that they approximate the rectangular Wilson loop. And then for the rectangular Wilson loop, people know,
So approximate.
so suppose this is the time direction,
Yes.
and these are, let's put time, and these are two sides, that is capital T and capital L. So we consider this configuration in the limit in which T and L are very large, and T is much larger than L. But this is nothing but the static potential that people computed in n equals 4, and also the strong coupling. So for this particular thing, both weak and strong coupling results are known, and it turns out that it's not in agreement with the BDS conjecture.
So that's the BDS conjecture for the endpoint amplitudes, but just where n goes to infinity
Yes.
in a particular way,
Yes,
with particular choices of the momenta.
yes. Very particular, those choices.
But that means for large lambda and large n.
Yes, yes, but with lambda larger than n. I mean, you take lambda to be very large, with n, little n is the number of gluons. So we are taking a large n limit.
Right,
Little n.
but presumably there, if you continue their formula where they established at weak coupling, you know that.
Well, we don't continue their formula, but we use an additional thing that is a duality between, at one loop, between Wilson loops and scattering amplitudes that I didn't have time to discuss. But just the message is that you can consider a very particular, besides 4 gluons, you can also find the solution for an infinite number of gluons, and you can test whether BDS works or not, and it seems it doesn't.
So now with the hindsight of these papers which explain why 4-point function and 5-point function are actually fixed by this dual
Yes.
conformal symmetry, it's very hard to believe that this formula should be true.
That's exactly. So that is one point. There is, well, this symmetry, this conformal symmetry, was seen to work also at weak coupling, right? And actually fixes the form of the amplitude for 4 and 5 gluons.
Right.
But there is no computations for more than 5 gluons, more than one loop computation. So BDS conjecture may fail. And actually this would suggest that it does fail.
In terms of results at strong coupling, is there now a 5-point function at strong coupling?
No,
Because
just
it's-
4, yeah.
Right. This is the only thing that's been done now at strong coupling is 4
Neat.
and infinity.
Yeah, like people try to do some kind of limits, but I would say so, yeah. Like you can compute corrections to this, but
But again, f of lambda n is infrared. So because of the dual conformal symmetry, the infrared is related to finite path. And that for some reason goes to 4-point function even factor.
yeah, but not for
But
higher.
that's why you should expect this relation for higher point function when there is no any symmetry relating infrared asymptotics to finite path.
Yeah, I must say that BDS conjecture, anyway, satisfies this factorization, many properties that are not trivial to satisfy, even for higher point functions. But this survives all that restrictions that we discussed with Byrne and Dixon also. So they agree that it may fail for n bigger or equal than 6. Yeah, there are many things I could say, but I think I can stop here also. Thank you.
Well, I guess since the last quarter now we're pretty much doing questions anyway, we should just head to lunch.
Yeah, please.
Sounds good.